So here we are in section 1.8, and it is inequalities. They often start out very similarly to equations. So if I wanted to solve this inequality, I'm going to first use my distributive property. And as we can see, I get this. And then we can really see that this inequality is linear because the highest degree of the variables is just 1. So in this case, my focus is going to be on, just like an equation, bringing everything that has an x to one side. If it doesn't have an x, I'm going to bring it to the other side. And I'll end up with x is greater than or equal to 6. So of course, this is the big thing. I have a greater than or equal to in the middle. This means that any value, any real number that is greater than or equal to 6 will make this inequality true. That's really the key thing here. So with an inequality, you could see greater than, you could see less than, you could see greater than or equal to, you could see less than or equal to. Any of those things are possible. In this case, greater than or equal to. Multiple ways we can write the solution. So it says solution here. Notice there's 4 different things here, 4 different ways we can do this. I'll tell you which ones are the most common. So inequality notation is what we just did. X is greater than or equal to 6. Set notation is the set of all x such that x is greater than or equal to 6. So it's just a slightly more mathy way to say what the solutions are. This is similar to when we did equations and we just said, okay, our answer is 5, we put it in a set with the brackets, or our answers are 2 and 4, and we put them in a set with brackets. But because there is a lot more than just one solution, 2 solutions, we have to do a little bit more with our set notation. So we'll see set notation more, but again, the idea, and you can write this out if you need to, is the way that this is read is the set of all x such that, that's the straight line, such that x is greater than or equal to 6. So that's how we read that in words. Graphically, we really just want to, that's not a straight line, but it's okay. I'm just going to put a few values here on a number line. That's the idea. And on a number line, what we do is we're just showing graphically with a line what solutions make this inequality true. So we're going to start at 6. I'll put a filled in circle. That tells me that 6 is also a solution since I have greater than or equal to. And because it's greater than, I have a arrow to the right to indicate everything greater than 6. So besides being 7, 8, 9, that's also 9.5 and 100.67 and 1,500,002. And so that line just tells us it keeps going and going and going. So set notation is used a lot. Interval notation is also used quite a bit once we get into higher level mathematics. And interval notation starts with the smallest number that makes this inequality true and goes up to the largest number that makes this inequality true. So the smallest number that makes it true, as we can see, is 6. We include 6, so we use this square bracket to include 6, and it just continues on and on and on. You can imagine that just keeps going. I could pick any number greater than 6, and that's going to be included as a solution, meaning it makes this inequality true. So that goes all the way up to infinity. I'm going to put a parenthesis, which is always used with infinity or negative infinity, because if you think about it, infinity is not a number. It cannot be included in the solution. So the parentheses tells us this value is not included. So if you want, you can take a moment and see if you can use the distributive property here, or see if you can isolate the x. You can go ahead and pause if you want to do that. So if you got here, the big question is, what do we do now? We know that, just like an equation, we'd want to isolate the x by dividing by -5. But here's a really big difference between equations and inequalities. we all could probably agree that 7 is less than 10. But if I divide 7 by -1, and I do that to the same, I do that as well to the other side, then what you're going to see is, dividing something by -1 just changes its sign. But notice that now we have -7 on the left and -10 on the right. And what we might recognize is, in fact, -10 is less than -7, because now we're on the other side of the number line. Because of that, anytime we multiply or divide by a negative number in an inequality, we need to flip the inequality sign. So we'll have x is less than -3. And we can write the answer there in multiple different ways, but we want to understand that, if we think about a number line, here's 0, here's -3. We're not going to include -3, we're only going to include everything less than. But when we think about less than -3, that includes -3.01 or -3.002. And so because of that, we don't put it at 4, because everything between -3 and -4 is included too. So that's why we put the whole at -3. Notice that this arrow is going to keep going on and on and on, meaning that the smallest value that makes this true is actually the idea of -infinity. You can kind of pick any large negative number. It's going to make this inequality true if you plug it in, all the way up to -3, and then we're not including -3 because of the not having an equal to sign in our inequality, and therefore I have that parenthesis. For compound linear equations, just notice this has 2 inequalities in it, 2. And so we can look at this as kind of 3 pieces. We have our first piece here, we have our second piece here, we have our third piece here. We're still trying to isolate this x. We still want x to be by itself, arguably in the middle of this set of inequalities here. So there's a couple different ways you can do this. You can create 2 inequalities. As we're getting into higher level stuff, I think it's easiest to just understand that if we want to isolate that x, we're going to want to move things, for example, that 1, so that it's no longer in the middle, but gives us the fact that 3x should be less than or equal to 12, greater than or equal to 6. And then I just got to do everything to all 3 sides here. Isolate that x, it tells us the x is less than or equal to 4, greater than or equal to 2. So any value between 2 and 4 is going to make this inequality true. That's the thing we want to remember. So as an interval notation solution, that's going to be from 2 to 4. Notice I'm putting the hard brackets around it because both 2 and 4 are included because of those equal signs in the inequalities. Now we have a very fun linear inequality word problem application, as we say. And so we have a car that is going to be rented from a car service, or could be, and it's $180 per week, unlimited mileage. Drive as much as you want. I'm sure you have to also, however, pay for your own gas, which is very expensive right now. A similar car can be rented from a different car rental place for $120 per week, but then you also have to pay 20 cents per mile driven. For what mileage is Zulu cheaper per week? So understand that these words are application words, cheaper, but it means when is Zulu, Zulu less than Acme? That's how we want to think about this. So for Acme, we're just going to make ourselves a linear equation and we're going to solve it. So Acme cost, as we know, is just a flat 180. Because Zulu has this 20 cents per mile driven, that means that it depends on the number of miles you drive. Well, that is a variable. So because we don't know how much it is, it's something that changes. So X will be miles driven. And we know that that's what we should call X because it's saying for what mileage is. is Zulu cheaper per week. So miles driven would be a good way to say that for X. So that means that Zulu cost is that flat 120. That does not change. It is 120. But we also have to pay 20 cents. We want to think about that as a decimal. So it shouldn't be 20. It should be 0.2. And then times the number of miles driven. So if you drive 100 miles, you multiply that by the 20 cents, and you can see that that's 20 miles. But we have these other costs associated too. So we want to know, when is Zulu less than Acme? So we have this. And now it just becomes a linear inequality. So you're welcome to solve it if you can. That would be great. Pause, go ahead and do that. Oops, got my X. Let's get that back in there. There we go. So this will give us X is less than 300. And so that's a number of miles. So this tells us that for what mileages is Zulu cheaper per week? For less than 300 miles driven, Zulu is cheaper. So not uncommon to need to write a sentence for an application problem to answer it. We don't want to just say X is less than 300. That doesn't mean anything to anybody because it's asking about the mileages. We want to say something about what the mileages are. So we get this as our answer for this application problem.